Here's part 2 of the entire grade 12 calculus course. In this part we're going to look at curve sketching. In order to do curve sketching, we're going to look at the connection between a function, its first and second derivative, and we're also going to do a couple optimization problems as well. So example 8. Find the absolute max and min values of f at x on the interval x being in between -3 and 5, including -3 and 5. So let's get a visual representation of what we're looking at for this question. Here's the degree 3 function, and we're interested in what is the highest or lowest this function goes on the interval between -3 and 5. Now, this function has no absolute max or min on its entire domain, but if we restrict the domain to being between -3 and 5, we'll see that this function does have an absolute min and max. The absolute min it ever goes is right here, and the highest it ever goes on that interval is right here. So how are we going to find and make sure we find those absolute max and min points? Well, in order to find them, we just have to test a couple different pairs of points. We always have to test the endpoints of the interval, so we have to figure out how high is the function when x is -3 and when x is 5. And then we also have to test any other critical points between those endpoints of the interval. Remember, critical points are points that make the derivative either 0 or undefined, because at this point right here the derivative would be 0 because it has a horizontal tangent, and right here the derivative would be 0 because it also has a horizontal tangent there as well. So let's make sure we figure out there's an absolute min when x is 2 and an absolute max on the interval when x is 5. So we have to test the endpoints and the critical numbers. So let's start by finding the critical numbers by finding the derivative of the function. So I'll differentiate the f at x function, and I get 6x squared minus 24. And now I need to figure out when is this function undefined or 0. Well, it can't be undefined, it's a quadratic, but it could be 0. And then I'll just solve this by factoring. I have a difference of squares, 6 times x minus 2 times x plus 2. And I see that there are two critical numbers. So my critical numbers are x equals 2 and x equals -2. So those are critical numbers. Those are the places where the derivative is 0, which means there's a horizontal tangent there, which means it could be a local max or min. It may be an absolute max or min as well. We'll have to test the endpoints and these critical numbers in the function. So the endpoints of the interval were -3 and 5, and there were two critical numbers in between there, -2 and 2. And then we just have to test each of those values in the function and see what their corresponding y values are. So we could just quickly get Desmos to calculate those for us. Now that they're all filled out, you can see that the lowest y value we ever have, right, the lowest the function ever goes, is right here, -29, and the highest the function goes on the interval is 133. So we can state our absolute max and min values on the interval now. Next example. Example 9. Consider the function defined by f at x equals -4x cubed plus 6x squared plus 2. What we're going to do with this function is find critical points and classify them as local max or min points using the second derivative test. And we're also going to find points of inflection and identify the intervals of concavity. So let's start right with part A, where we have to start with finding critical points. And before we can find critical points, I need the critical numbers, which are numbers that make the derivative either 0 or undefined. So I need to find the derivative of f at x, which would just be -12x squared plus 12x. That's my derivative, so I'm interested in when is this undefined or 0, and that's a critical number. Now this can't be undefined, it's just a quadratic, but it could be 0. And I'll solve it by factoring, so I'll common factor out a -12x. And I'm left with x minus 1 when I divide both of those by the -12x I factored out. And now this product could be 0 if either that factor was 0, which would happen if x was 0, or if this factor was 0, which would happen if x was 1. So I have two critical numbers. But the question says we need critical points. Critical points involve the x and y coordinate. So I need the y coordinate that goes with each of those x coordinates. So I'd have to evaluate what is f at 0, what is f at 1. My critical points are the point 0, 2, and 1, 4. So let me show you visually on a graph what we have found so far. We have found that point 0, 2 and 1, 4 are potential local max and min points because they have horizontal tangents. We figured out at this point the first derivative is 0, and you can see that here. And we also figured out that at this point the first derivative is 0. So we figured out their potential local max or min points. But what we need to do, since we don't have the graph, is we actually need to classify them, and I said to do that using the second derivative test. What's that? Basically, we're trying to figure out, at these points, is the function concave up, which would mean that we have a local min, because there's a horizontal tangent, or is it concave down, which would mean that we have a local max, right? There's a horizontal tangent there, concave down would mean a local max. There's a possibility as well that maybe we have something like this. There's a horizontal tangent there, but the function is neither concave up nor down there, so the second derivative test would fail, and we would have to use the first derivative test to check if it was a max or a min, or neither. So let's do the second derivative test. Let's actually find the second derivative, f double prime of x. So I need to find the derivative of the first derivative. So I need the derivative of this function, which would be negative 24x plus 12. And then I need to use this equation to figure out if the original function is concave up or concave down at these 2 points. And I can do that by plugging in the x values, the critical numbers, so f double prime at 0 and f double prime at 1, to figure out if the original function is concave up or down at those 2 points based on the sign of the value of the second derivative. Right, when I plug in 0, I would get 12. That's positive. So the fact that that's positive tells me that the original function, f at x, is concave up at the critical point. So at point 0, 2, f at x is concave up. What does that tell me? It tells me 0, 2 is a local min, right? If it's concave up and has a horizontal tangent, that means it looks like this. Now let's find the value of the second derivative at the other critical number when x is 1. So if I plug that into the second derivative, I will get negative 12. And the fact that that is negative indicates to me that f at x at that point is concave down. So f at x is concave down at the critical point 1, 4. That means that 1, 4, since the function is concave down and has a horizontal tangent there, is a local max, max. So we were able to classify those 2 critical points as local min or maxes using the second derivative test. Let me just show you again what we figured out. We figured out that right here, it has a horizontal tangent, right? The first derivative is 0, and the second derivative is positive, meaning it's concave up, which means we have a local min at that point. And at this point, we figured out that the first derivative is 0, indicating a horizontal tangent, and since the second derivative is negative, we know it's concave down at that point, which means that's a local max. Okay, part B of this question asks us to find the intervals of concavity and any points of inflection. So what we're looking for now, we're looking for, first of all, when is the function concave up? And we can see from the graph it's concave up, right, when it opens above the tangent line that's drawn. So it's concave up until right there. And then the function starts to open below all these tangent lines. So then it's concave down for the rest. So it's going to be concave up before 0.5 and concave down after 0.5. We're going to figure that out algebraically though. And notice at 0.5 there's a switch in concavity. We call that a point of inflection. So we want to find all of this algebraically. So to find the intervals of concavity and the points of inflection, we're going to start by finding things called possible points of inflection. And possible points of inflection are points where the second derivative is either 0 or undefined. Remember the equation of the second derivative, we had that from part A, was f double prime of x equals negative 24x plus 12. So that's going to tell us the concavity of the function at any point we want. Let's figure out when this is 0 or undefined, and that's a possible point of inflection. That's a point where maybe the function might be switching from concave up to concave down. So let's set it to 0 and solve. And this is just a linear equation to solve. So I could just rearrange this and get x equals a half, right, 0.5. So that's a possible point of inflection. Actually, I should get the y coordinate that goes with it as well. So f at 0.5, notice the y value is 3, and we can get that by plugging it into this equation. And I have Desmos doing that for me right now. So f at 0.5 equals 3. So our possible point of inflection is point 0.53. So that's a point where the function might switch from being concave up to concave down. What we're going to do to test if that actually is a point of inflection is we're going to make a chart where we test the value of the second derivative around that possible point of inflection. So our possible point of inflection was at 0.5, and we're going to pick a point or an x value on either side of that possible point of inflection and see what does that do to the value of the second derivative. Does it make it positive or negative? And what does that tell us about the original function? So I'm going to pick a point to the left of 0.5. So how about negative 1, and a point to the right, how about 2? And let's plug those into the second derivative. Well, here's our second derivative right here. If I plug -1 in, I would get 36, which is positive. And if I plug 2 in, I would get -36, which is negative. So that tells me that the original function is concave up in that interval. It's concave up. And in this interval, from 0.5 to infinity, the function is concave down. So it switches from being concave up to concave down at this point, 0.53. So what we have right there is a point of inflection at 0.53. We just verified that by seeing there's a switch in concavity. And I could also summarize the intervals of when the function is concave up and concave down by looking at the table here. So it's concave up for x values less than 0.5 when x is less than 0.5, and it's concave down when x is greater than 0.5. And let's just verify that from the graph, right? It was concave up before 0.5, right? The second derivative values, if we look here, are always positive before 0.5. But after, and at 0.5, the second derivative is 0, right? That's our point of inflection. And after 0.5, all of the second derivative values, if we look at them, they're all negative. And just to make sure you understand the connection between the first derivative and second derivative, the first derivative tells us the tangent slope, right? They tell us the slope of that green line. The second derivative tells us how the first derivative is changing. So it tells us how are those tangent slopes changing. Well, if we look on the interval from -infinity to 0.5, look what's happening to the tangent slopes. Look at these numbers. Notice that they're getting bigger. They keep getting bigger, 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 all the way up to the highest they get is 3. And then after 0.5, what happens to those first derivative values? They get smaller, right? So that's why before 0.5, the second derivative is always positive, because these numbers are increasing, right? And this number tells us how these numbers are changing. So the second derivative is positive until 0.5 because the tangent slopes are increasing, and then the second derivative is negative after 0.5 because the tangent slopes are decreasing. Okay, let's do a curve sketching question. Example 10, sketch the following function using the algorithm for curve sketching, which is, this algorithm is just a list of steps that gets us key features of the function, including intercepts, max and min points, intervals of concavity, points of inflection, and so on. So I'll walk you through the algorithm for curve sketching, and we'll get an accurate graph of this function here. So we're going to start off by looking at, does this function have any asymptotes? Well, this is just a polynomial function. Polynomial functions don't have restrictions on their domain. There's no asymptotes for polynomial functions, so for this function, there are none. Intercepts. So let's start with the y-intercept. That's easier. We'll do x-intercepts after. So y-intercept, all we have to do is figure out the value of y when x is 0. So we'll evaluate h at 0, and we would get 4. So our y-intercept is at the point 0, 4. X-intercepts are a little more difficult to calculate because we have to figure out what value of x makes the y value 0. So we want to set this function to 0 and solve for what value of x makes that true. And for this function, it's a degree 3 function. So we're going to have to get this in factored form to find its zeros. So grouping doesn't work for this one, so I'd have to actually test for zeros by testing factors of 4 to see what makes it be 0, and then I'll do some synthetic division. And I think -1 makes this become 0, so if I do synthetic division where I divide it by x plus 1, right, I'll put my 0 of the divisor right there, and put the coefficients of the polynomial here, 1, 6, 9, 4. I'll quickly do synthetic division, bring it down, multiply, add, multiply, add, multiply. There we go. These are the coefficients of my quotient, right? There's my remainder. Here's my x to the 0 term, my x to the 1 term, my x squared term. So I figured out that this can factor into x plus 1. And I got that from figuring out that -1 makes this be 0. And x squared plus 5x plus 4 is the quotient. So there we go. So this factors into those two factors. And that quadratic that I got as my second factor could factor further into x plus 4 times x plus 1. I've got x plus 1 twice, so I could just write that as x plus 1 squared and x plus 4. So I only have two x-intercepts. What would make this product become 0 is if either x was -1 or if x was -4. So I have two x-intercepts, one at -1 and one at -4. So two x-intercepts. So the next step in the algorithm for curve sketching is finding critical points, right? Finding points that are potential local max or min points on the function are going to be important when drawing its graph. So for critical points, I need to start by finding critical numbers, which would mean I need to find numbers that make the derivative be either 0 or undefined. So I'm going to have to start by differentiating this function. So I would get 3x squared plus 12x plus 9. 3x squared plus 12x plus 9. So that's the equation of the derivative of h at x. And a critical number would be a number that makes this 0 or undefined, but that's a quadratic, can't be undefined, but it could be 0. Let me solve it by factoring. And then I see that that quadratic could easily factor to x plus 3 times x plus 1. And I have two critical numbers, right? My critical numbers would be -3 and -1. Now that I have my critical numbers, I need the critical points, which means I need to know the y-coordinate that goes with each of those x-coordinates on the original function. So I have to evaluate h at -3 and h at -1. So I have two critical points, -3, 4, and -1, 0. So those are my critical points. So those are points that might be local max or min points. We'll have to, when we get later in the algorithm for curve sketching, we'll be able to actually classify them whether they are local max or min points or neither. Step 4 in the algorithm for curve sketching is where we find possible points of inflection. So to find possible points of inflection, we have to find x values that are going to make the second derivative 0. So I need to start by finding the equation of the second derivative. So my first derivative is here, so if I differentiate that, I get my second derivative, so 6x plus 12. So h double prime of x equals 6x plus 12. And then I'm looking for what would make that be 0, and that would be a possible point of inflection. So 0 equals, I'll just common factor that so I can see that the solution is -2. Now I need to find the y-coordinate that goes to this x value, so I'll plug -2 into the original function. So h at -2 is 2. So at there's a possible point of inflection at -2, 2. So let me just show you a visual representation. I know we don't have the graph yet, but let me just show you what Desmos shows us, just so you're on track with what we found out so far. So we have found out that we have, at this point here, when x is -3, we know the first derivative is 0, so it might be a local max or min. When x is -1, we found out the first derivative is 0 there as well, which means we might have a local max or min. And we also found out right here the second derivative is 0, which means that might be where, second derivative 0, that might be where the function switches from being concave up to concave down or vice versa. The last step of our curve sketching algorithm, before we actually graph it, is we're going to make this big chart where I'm going to test my critical numbers and my possible point of inflection to figure out what that does to the first and second derivative, and therefore what does that tell me about intervals of increase, decrease, intervals of concavity for the original function. So in the table, you're always going to put -infinity and infinity on the far left and right. And then in between, you're going to put all your critical numbers and possible points of inflection. And then we're going to choose test points within each interval I've created here. So between -infinity and -3, I'll choose -4. Within this interval, I'll choose -2.5, -1.5, and anything between -1 and infinity, how about 0? We'll test each of these in the first and second derivative and just see whether we get a positive or negative answer. So if I plug -4 into here, I'd get a positive times a negative, that's positive. If I plug -4 into the second derivative, I'd get a positive times a negative, that's negative. So what that tells me, since the first derivative is positive, I know that the original function is increasing. Right? The sign of the first derivative tells us whether it's increasing or decreasing, and the sign of the second derivative tells us that it's concave down. So we have an increasing function that's concave down. So it looks something like this. When I plug -2.5 in, I get positive, positive, negative, so that's negative, so it's a decreasing function. And into the second derivative, I would get positive times negative, that's negative, so it's concave down. So I have a decreasing function that's concave down, so it looks like this. Plug -1.5 in, negative, that's negative. Plug it into second derivative, positive times positive is positive. So I have a decreasing function because the first derivative is negative, that's concave up because the second derivative is positive. So I need a decreasing function that's concave up. It's going to look like this. And lastly, plug in 0, makes the first derivative positive, makes the second derivative positive, so I have an increasing function that's concave up. Increasing concave up looks like this. So there's a local max at -3, 4, and I know that because the function was increasing before -3 and then decreasing after -3. So it looks like this, so there's a local max at the point. And I know there's a local min at -1, 0, and I can tell that because the first derivative tells us the function was decreasing before and increasing after, which means there is a local min. At this point here, I know there's a point of inflection because there's a change in concavity. The second derivative changed from concave down to concave up around the x value of -2. So at -2, 2, we have a point of inflection because there's a change in concavity. Now let's use all of this information to sketch an accurate graph of the function. So I'm going to start by plotting all of the points I have. So I had my x-intercepts at -4, -1, y-intercept at 4. I had critical points at -3, 4, right? We figured out that was a local max. We figured out there was a local min at -1, 0. And we figured out there was a point of inflection at -2, 2. And then if I match up my intervals of increase and decrease and my intervals of concavity based on what it says here, I would have increasing and concave down in this interval, decreasing and concave down in this interval, still decreasing but now concave up in that interval, and now increasing and concave up in that interval. So there's my graph of h at x. I missed that y-intercept a little bit, but that's relatively accurate graph of that function h at x, right? We have the right local min, right local max, we have the correct point of inflection, the correct intercept, so that's a very good graph of the function. And if we compare that to what Desmos gives us, you'll notice we have the correct intervals, right? And as I'm sliding this point along, look at the first derivative. Right here, that tells us whether the original function is increasing or decreasing based on whether it's positive or negative, and the value of the second derivative tells us whether it's concave up or down based on whether this is positive or negative. So notice increasing and concave down in that interval, decreasing and concave down in that interval, decreasing and concave up, then increasing and concave up. Example 11, let's try an optimization problem. Aisha is making a jewelry box for her mother in tech class. The top and bottom of the box will be square, made out of a wood that costs $0.002 per centimeter square. And the sides of the box will be made from a cheaper wood that costs $0.001 per centimeter square. Find the dimensions of the box that will minimize the cost if she wants the box to have a volume of 4,800 centimeters cubed. An important thing to note here is that this jewelry box is a square-based prism. So I want you to visualize this problem. GeoGebra drawing this jewelry box for us. Notice it says the jewelry box has to have a volume of 4,800 centimeters cubed. So as I adjust the dimensions of this box, notice that the volume is staying steady at 4,800 centimeters cubed. But as I'm adjusting the length, also notice that the height is adjusting accordingly to keep that volume steady at 4,800 centimeters cubed. We want to figure out which of these boxes, what dimensions could I make that would minimize this cost here. So we're going to have to generate formulas that are going to optimize the cost when making this jewelry box, using the constraint that the volume has to be 4,800 centimeters cubed. So what should the dimensions be? So this is our box. Keep in mind we want to minimize the cost, and cost is based on the surface area of the sides. So I'll start by generating a surface area equation for a square-based prism. Let me just label this jewelry box here. It says it's a square base, so I can label these dimensions with the same variable. I'll call them both x, so the length and width of the base are both x. And then here's the height of the jewelry box. The surface area would be the area of all of these sides added together. Well, the top and bottom are both x by x, so the top and bottom are both x squared. Add them together, I get 2x squared. And all four of the sides of the box are all x by h. So I have 4 sides, so plus 4xh. So here's the surface area equation for any square-based prism. What I want to do is generate a surface area equation for a square-based prism that has a volume of 4,800 centimeters cubed. So the question gives us that constraint. So the constraint the question gives us is that the volume, which is represented by area base times height for a prism, so x squared times h, has to be 4,800 centimeters cubed. So 4,800 equals x squared times h. So now I can generate an equation that shows me the relationship between the height and the length and width of this square-based prism by isolating for h. So h equals 4,800 over x squared. So based on whatever the length and width are, I can calculate what the height would have to be to keep the volume steady at 4,800 centimeters cubed. So what I can do now is replace h in my surface area equation with what I figured out h is equal to keep the volume at 4,800 centimeters cubed. And now what I have is a surface area equation written in terms of one variable. And that's always our goal when we're doing these optimization questions, is generate an equation based on one variable using the constraint given. So I have 2x squared plus 4 times x times what h is equal to written in terms of x, which is 4,800 over x squared. So this is the surface area equation. If I was interested in minimizing the surface area, I could just find the derivative of this, set it to 0, solve. But I'm interested in minimizing the cost, right? The top and bottom, so keep in mind this tells me the surface area of the top and the bottom of the jewelry box. And the sides of the box cost different amounts. So the top and bottom cost $0.002 per centimeter square. So if I want to generate a cost equation, because I'm interested in minimizing the cost, I would have to multiply the surface area of the top and bottom by 0.002, and I would have to multiply the sides by 0.001, because that's what the surface area of the sides cost per centimeter squared. So now I have the cost equation written in terms of x. So a cost equation written in terms of one variable, I could figure out any local max or min points of this by finding the derivative, setting it to 0, and solving. I'll simplify this first before I bother finding the derivative to make it easier. So I've got 0.002 times 2, that's 0.004 x squared, plus I've got 0.001 times 4 times 4800, that's 19.2, and I have an x divided by an x squared, so that factor of x will cancel with one of those factors of x. I'm left with x to the 1 in the denominator. Bring it up to the numerator. I've got x to the negative 1. Okay, so I'm interested in when is this function at the minimum point. I want the minimum cost. Well, I know at the minimum cost, there's going to be a horizontal tangent. So I need to figure out when is the derivative equal to 0, because that will indicate there's a horizontal tangent at the original function. So I have to find the derivative. So I'll differentiate this using power rule. 0.008x minus 19.2 x to the negative 2, and then I'll set this to 0 and solve. And now I just have to solve for x. I'll take this term, move it to the left side, and then I'm going to multiply this power of x squared to the right and divide that coefficient of 0.008 to the left. So I just have to evaluate this quotient and then cube root it to isolate x. So x is about 13.4. And we're in centimeters. So at 13.4, what we figured out is there is a horizontal tangent, which means we quite possibly could have a min point, or we could have a max point, or we could have neither. We have to verify that it's in fact a minimum point of the cost function. We could do that using the second derivative test if we want. We could do second derivative test, or first derivative test, or we could just check the endpoints of the function. But I'm going to do the second derivative test, find the derivative of this function, and then I'll plug that critical number which we found, which was 13.4, into the second derivative, and hopefully we get a positive number indicating that the function is concave up and has a horizontal tangent there, which means it would be a local min point, which means we have found the dimension that gives the min cost. So if we evaluate the second derivative at 13.4, we would get approximately 0.024. So the important thing there is that the second derivative at 13.4 is positive, it's greater than 0. Therefore, the cost function is concave up at that point, which means the point 13.4, cost at 13.4, is a local min. Now we can answer the question. The question says, what dimensions minimize the cost? It doesn't actually ask us for the minimum cost, but if we wanted it, we could just plug 13.4 into the original cost equation. It just says what dimensions minimize the cost. So the length and the width, we called those x, and we figured out that that's about 13.4. If we want to calculate the height, we know the height was equal to 4800 over x squared. That was based on our constraint. So if we do 4800 over 13.4 squared, we'll get an approximate dimension of the height that would minimize the cost, which is about 26.73, and these are in centimeters. So those two dimensions would minimize the cost. Let's just verify that with the GeoGebra demonstration. So we figured out the length of 13.4. So this is going to minimize the cost, and it turns out the minimum cost is 215. Let me adjust the dimensions and make sure we don't get a cost below 215. Yeah, it looks like 215 is the lowest it will go, so we found the correct dimensions that minimize the cost. So that's the end of part 2. Make sure you click on to part 3 so you can learn about derivatives of exponential functions, logarithmic functions, and trig functions.